In this video, we're going to explore the ins and outs of sketching circular functions. We'll start with an overview of the key properties of circular functions, and then we'll look at how we can use those key properties in order to sketch the graphs of sine and cos. And finally, we're going to throw all those rules out the window when it comes to sketching tan graphs. Let's get to it. There are two basic shapes of circular functions. First, let's look at sin x. It creates this sort of wave-like pattern which will continue forever if the domain isn't restricted. When it comes to graphing circular functions, there are a few key properties that you'll need to be aware of. First, we have the peak and the trough. The peak is the maximum value of the circular function, and the trough is the minimum value of the circular function. Circular functions in math methods will often have more than one peak or trough, because as we said before, they'll continue on forever unless we restrict the domain. The mid-level of a circular function is the midpoint between the peak and the trough, and you can find this by using the midpoint equation. The mid-level is also given by the c term of the general form, which in the case of sin x must be 0 since the c term is absent. If you aren't yet familiar with the general form, don't worry, just click the link above and it'll take you to a video which explains all these concepts in detail. I'll even leave the link in the description for you. Moving on to the amplitude. The amplitude is the distance between the midpoint and the peak of a circular function. You can find this distance by subtracting the height of the peak from the height of the mid-level. And in the case of sin x, this gives you the value of 1. This is where students get caught out a fair bit. The a term in the general form is not the same thing as the amplitude of that circular function. It will always have the same numerical value as the amplitude, but the amplitude must always be positive, whereas the a term can be positive or negative. The sign at the front of the a term just tells us if the graph has been reflected or not. And reflecting the graph does not change the height of the peak or the height of the mid-level. So the amplitude will always be the same, regardless of if it's been reflected or not. And the last key property that you'll need to be familiar with is the period. The period of a circular function tells you how long it takes for that circular function to complete one cycle. And it's given by 2 pi divided by n, where n is the dilation factor in the general form. Okay, well that was the graph of sin x, but what about the graph of cos x? The graph of cos x is almost identical to that of sin x. In fact, if you shift the graph of sin x back by pi on 2, you'll actually get the graph of cos x. In fact, another way to express cos x is just sin x plus pi on 2. Because of this similarity, there aren't actually any new key properties that we need to be aware of. When it comes to graphing these functions, this subtle difference tends to trip people up. And this is because they're taught as two separate graphs. But if you follow the process that I'm going to outline, the difference won't matter. Now that we know the key properties of sine and cos, let's have a go at sketching them. Here's the process that we're going to be running. I know it looks like there's a lot of steps at the moment, but you'll find as you go through it that a lot of these steps only take 1 or 2 lines of working to complete. So let's give it a shot. The first step is to ensure that the equation is in the general form. Now, our equation already is in the general form, so we don't have to worry about this step. It's important to note that it doesn't matter if it's sine or cos, either is fine. To make things as clear as possible, I'm going to rewrite the equation like this, so that it looks identical to the general form, rather than the simplified version. This level of detail is not at all required for your exam, it's just here to illustrate a point. Next, we can identify some of the key qualities of this circular function. The first one we'll start off with is the period. The period is given by 2 pi divided by n, and we can clearly see that n equals 1, hence the period must be 2 pi. The mid-level of the circular function is just the c term, which in this case is 0. The peaks and troughs of a circular function occur at c plus a and c minus a, which in this case gives us a peak of 1 and a trough of negative 1. Now that we have these key values, where do we put them? That's where step 3 comes in. This first step handles the case if our circular function is a composite function. This isn't applicable here because this first example is a bit simpler, but it will be applicable in the more complicated next example. In the previous steps, we found the y values of each of these key features. This next step is going to show us how to get the corresponding x values. And we do this by subbing in our known y values into the circular function and solving for x. After subbing in all of our known values and rearranging, here's what we get. If we want to find the mid-level, we need to solve cos x equals 0. If you want to find the peak, you need to solve cos x equals 1. And if you want to find the trough, you need to solve cos x equals negative 1. And you need to solve all of those functions over the domain 0 to 2 pi. Looking at the unit circle, we can find the following. cos will be maximum when it equals 1. And we can see this occurs when x equals 0, and again when x equals 2 pi. Cos will be minimum when it equals minus 1, and this occurs when x equals pi. Cos will be at its mid-level when it equals 0, and this occurs when x equals pi on 2 and 3 pi on 2. We're going to skip the third step because it only applies if the circular function is a composite function. Now that we have our solutions, it's a good idea to double check the domain. Our domain is from 0 to 2 pi, and so are our solutions. So we're good here. Now we actually have all the information we need to sketch our graph. Let's give it a shot. We're going to start by dotting out all of the key features. Starting with the mid-level, we know that the mid-level occurs at pi on 2 and 3 pi on 2, and it has a value of 0. We know that the peaks occur at 0 and 2 pi, and that they have a value of 1. And we know the trough occurs at pi and has a value of negative 1. Now all we have to do is draw a nice little curve that connects all of these dots. But pay close attention to the domain. If the domain has square brackets, then it means that the endpoints must be closed circles. If the domain has open brackets, then those endpoints must be open circles instead. Now we can look at something just a bit harder. First, we're going to rearrange into the general form. And we do this by taking out a common factor of 100 pi from the inside. And we're going to do this because in the general form, x has no coefficient. The end term must be on the outside. Next, we're just going to rewrite the horizontal translation to be a subtraction rather than an addition because that's what's said in the general form. That part was actually a bit overkill, but while you're learning, it's good to get used to these kinds of rearrangements. Next, we're going to quick fire grab some of the immediate quantities. The period is given by 2 pi divided by n, and since n is 100 pi, that gives us a period of 0.02. The mid-level is just a c term, so it must be 80. The peaks and troughs are going to occur at c plus minus a, which gives us peaks at 100 and troughs at 60. Notice this time that the peak was actually given by subtracting a rather than adding it. This is because the peak must always be the maximum value, and when you subtract a negative value, you actually get a larger number rather than a smaller number. Now, let's find the corresponding x-coordinates. First, we can see that this equation is actually a composite function. So we're going to make it easier by applying a substitution. Don't forget to also apply this substitution to the domain. And since we're told to sketch over 2 cycles, and we know that one cycle is 0.02, our domain must then be from 0 to 0.04. To write this domain in terms of k, we're going to substitute the lower and upper bound of the domain into our k equation. Subbing in 0 gives us k equals 3 pi on 2, and subbing in 0.04 gives us k equals 11 pi on 2. Now, we're going to find the k values of each key point by setting up our equations. We're then going to simplify these equations into exact values expressions that we can solve on the unit circle. Notice how the peak now occurs at -1 rather than +1? This is because our circular function is actually reflected in the x-axis. That's the advantage of doing things this way. You only need to learn one process and you can handle all sorts of variations of this kind of question. Anyway, now that we have our exact values expressions, let's solve them. Let's start by finding the mid-values. Sine k is 0 when k is 0 or pi, but look at our domain. Firstly, our lower bound is 3 pi on 2, so we're going to end up discarding both of these solutions, but we'll leave it here for now. Secondly, we have an upper bound of 11 pi on 2, which as a decimal is 5.5 pi. Rounding up to 6 pi, this means that we need to go around the unit circle 3 times in total to get all the valid solutions, since one revolution is equivalent to 2 pi. This is done by adding 2 pi to our previous solutions of each revolution. Once we have our solution set, double check the domain to ensure that all of our solutions fit in and that we aren't missing any. This is where we remove 0 and pi from our solution set. Now we have to do this for the other 2 equations. It looks like a lot for now, but I promise this gets easier as you practice. Now for the max values. Sine k is -1 when k is 3 pi on 2. Again, we're going to add 2 pi to this solution until we find all the solutions in the domain. And lastly, we're going to find the min values by solving sine k equals 1 over the domain. Now that we have all of our solutions in terms of k, we're going to rewrite them in terms of x because that's what our question is expecting. We're going to do this by subbing in all of our solutions into the expression for k and then rearranging for x. To make things look a little nicer, I'm going to rewrite these as decimals, But when you're actually doing this arithmetic, I recommend you stick to fractions because it tends to be a lot easier to do math with fractions rather than decimals. And as a side note, this level of arithmetic isn't uncommon in your exam. In fact, the 2023 Tech 3 exam did have a strong focus on arithmetic, and the arithmetic was a lot harder than this. Now we just need to dot it out and draw a curve through it. So starting at the mid-level, now the peaks, now the troughs, and finally we'll draw a curve connecting all of those dots. Tan x has a strange looking graph. This is because tan x is actually sine x divided by cos x. The reason we get these vertical asymptotes is because the denominator can go to 0. If we look at the unit circle, we can see that cos x goes to 0 at pi on 2, 3 pi on 2, so on and so forth, and sure enough, that's actually where our asymptotes are. But the good news is because of this strangeness, tan x actually has less key properties to keep track of. First, it still has a mid-level. The mid-level of a tan function is just the point of inflection, and this is given by the c term in its general form. The period of tan x is still the time it takes to complete one cycle, but this time it's given by just pi on n rather than 2 pi on n. Why? Well, it's because of what we talked about earlier with those vertical asymptotes. Cos x goes to 0 twice within a period. Hence, the period of tan must be half that of the period of cos. So since the graph of tan x is so different to that of sine and cos, we have a new process to follow. Let's go through it. The first step, as always, is to rearrange into the general form. This function already is in the general form, so happy days. The next step is to split tan into sine divided by cos. Fairly simple. The next step is to find the inflection point, which is just the c term. And since the c term is absent, we know that the inflection point occurs at 0. Now, we want to find the asymptotes, which we can do by solving cos 3x equals 0 over the domain of negative pi to pi. This is just like solving a circular function, so we're going to follow the process. This is just like solving a specific solution to any other kind of circular function. Step 1 is already done for us. Again, we have the general form already. The next step, we can see that cos 3x is a composite function, so we're going to substitute u equals 3x and apply that substitution to the domain as well. Now we can use the unit circle to solve this equation over our given domain. Cos u is 0 when u is pi on 2 or 3 pi on 2. Extending this pattern over our given domain gives us the following solutions. We're then going to substitute u equals 3x back into the equation and rearrange for x to get everything back in terms of x like the question expects. Okay, now that we have the location of our asymptotes, we need to know the rough shape of the graph. We can do this by looking for any reflections in our graph. We can do this by looking at the a and n terms and seeing if there's any minus signs applied to them. We can see that only the a term has a negative sign applied to it, so we have a reflection in the x-axis. Normally, tan x ascends from left to right. It gets larger as it goes from left to right. If it's reflected in the x-axis, it's going to now descend. It's going to get smaller from left to right. Now that we have everything we need, let's start plotting. We'll start by putting in the asymptotes. Now, we're going to ensure that we put our inflection points at y equals 0. And finally, we're going to draw the curve descending from left to right. If you found this video helpful and would like to see more, I actually have written versions of these lectures available for free on my website. Just click the link in the description below and it'll take you to my website. Just scroll down a little and click this heading to get access. No opt-in required, free of charge.